All right, we'll continue on the perceptron learning part of that. As last session, I showed you the algorithm for perceptron learning. The step 7 to 9 are crucial, right? So it's a repeated operation. For what you can do with the perceptron is, you'll be able to classify objects that are in the linear space. Okay, and one more thing is the objects that we are going to be classifying should be linearly separable as well, right. So, once we satisfy this condition, it is possible for you to use the perceptron. So, remember in this perceptron we have only one neuron, even though we have neurons in the input space, they just pass on the value and only the computation is happening in this space, right. So, this is where we do the computation. So, we get the value of h and then we run it through an activation function and then finally, the output is computed. As I mentioned earlier, we are not going to be just using one input, we are going to be having lots of input in order for you to classify like we had shown here, correct. So, in order to create this boundary, you can either start with just one and then start learning that, or present the input completely. So, this is what we saw in the previous session. Okay, all right. So, now let us take a very small example and then see how perceptron behaves. Okay. Since this is a linear classifier, we are going to be taking a logical AND, right. So, we have the values here as 1, this is our 0, we have x1 and x2. Okay. In the AND operations, we have zeros here at 0 0, 1 0 and 0 1, and then we have a 1 here at 1 1, right. So, let us see whether the neural net is able to compute this. So, in this case the weights that are presented here are already learned. Okay. To help you understand that the perceptron really creates a linear boundary, I am just using the weights. So, this is one of the many combinations that you will find in the weights. Okay. There could be several combinations of the weights. It need not be -1 for the bias connecting to the neuron and then 1 connecting the x to the neuron and so on. So, it could be any number. So, in this case let us take those inputs. Let me first write this and then start combining this. So, this is 0 and 1 plus 0 1 plus and B is -1, right. So, that means when the value is less than or equal to 0, we are going to make it 0. Okay. So, now let us take this one 0.1 plus I am doing a multiplication 1.1 plus. Okay. So, this is again a 0, right. In the same fashion 0 and here it is 1.1 plus 1. So, this is 1. So, it is actually separating these from the real value, right. So, we have elements here on the side below this decision boundary and there is one element which is 1 1 for this. So, our perceptron really classifies this, it is able to solve this problem. So, in the same fashion I am not going to be doing this for R, you can do this. Again in this case you should be able to separate the 0 out. These are all values using a straight line in this fashion. Okay. So, try this operation and then using the weights given, try to find out it is really linearly separating this. Okay, let us take one example from the natural language processing and then see how we could create a linear boundary between positive and negative sentiments. So, the idea is to really draw a boundary so that all the positive sentiment words are on the right side of this boundary and the negative sentiments on the left side of the boundary. Okay, so, in this website you have lots of data related to words. So, we have word embedding. So, we will talk about that in the next lecture or so. So, how the word embedding could be obtained using one-hot vectors. Okay, so, we will talk about that later, but assume that we have captured this in some fashion. So, let us assume that instead of 0 or 1 given as the input, let us use the word embedding which contains values in this fashion. Let us say your one-hot vector would be like this. If you take some positive word, so this is your one-hot vector, and then word embedding for the same thing would be like this. Okay. So, this is a word embedding vector that contains about 50 elements. I am only taking the lowest possible, so that the computation can be done lot faster. So, you have up to you have 50, 100, 300 word vectors are available as part of the GLOW implementation. So, what they have done is they have taken close to 1 billion words and then provided the rather the word embeddings for each of the words that they have computed. So, this we can use as your input. Okay. So, in this case we are going to be taking the positive or negative reviews and then trying to classify them, right. And then we also require the positive and negative words for training. So, in here what I am doing is, for the sake of convenience, I have downloaded positive and negative words. They are about 6,000 in number. Again, these are available as open source, you can capture them. So, what they have done is they have classified a set of words as positive words, set of words as negative words, and you can take that. And one more thing that you may have to do is you have to do some input preparation. So, out of these 6,000 words, it is either possible or not possible to find those words in the word embeddings that are available from the GLOW website. So, make sure that the words that you are taking are present in the embedding. That is one of the most important thing that you have to do, right. So, I have taken those 6,000 words from the website, from some website. I am sorry I have not listed it here, but you can search for positive or negative words. You will find at least a couple of websites listing those words, and then take each one of them and try to find out whether the word embedding is available or not. And then again you get one more collection which could be equal to 6,000 or could be less than 6,000 words. Okay. So, that does not matter. So, for the sake of our understanding, even if you get about 5,000 words from the word embedding, and if they are matching, that is good enough for us. I am going to be using that set of words as input for this application. Okay, so this is what I explained. I need to generate the training data set first. So, what I am doing is I am just taking the positive words and then creating creating a list. In the same fashion, creating a list here as well, and then using the GLOW data, I am actually separating them out. So, when I do this, what I create is I just create a vector which is coming from the GLOW, and I know that it is a positive word or a negative word, okay. And then I attach that element 1 or 0 to the end of that. Okay. So, in this way I am creating the dictionary of words and then start building that model. So, how do you build the model? So, build the model using the training data X and the class associated with each word in the embedding. Okay. You normalize the values. Sometimes it is required, sometimes it is not required. I am just doing the normalization of this using a function called normalize feature values. And then I do the initialization of the weights that we have here. These weights I am initializing and then start computing the predicted output and then find the errors. Since I know what is the value of the word, right, with respect to the sentiment, I find out whether it is close enough or not close enough. If it is not close enough, I compute the error and then adjust the weight, so that in the next iteration it becomes closer to the actual value. Okay. Create the cost function. Cost function is actually the sum of all the errors that you are getting every time, right. So, when you are running through the entire EPO, for every word there is a loss created, okay, with respect to the actual target value and the predicted value, and then you keep adding that error into the cost function. Okay. And then finally, build the model wherein your W's are computed appropriately. Okay. And then once the weights have stabilized, so that is when the perceptron is able to predict the new input that you are going to be feeding in. You do the normalization very similar to what you had done during the model building, and then test the embedding word, right. So, you take one word from the embedding and then feed that and then find out whether the classifier really predicts the right value or not. So, in this case it has predicted. So, I think I have run close to about 500 to 600 iterations for all the input words. And then when you see that the cost becomes closer to some value, so you set a threshold value. Okay, if the value is less than this, stop the iteration, or if you think that it is good enough, it is not going to improve beyond the point. For example, you will see some flattening happening in this fashion. So, when you see that the error between the previous and the current one is extremely small and it is not improving further, you can stop, or you can keep a fixed iteration number or the EPO number or repo count and then stop the iteration at that point in time. Okay. So, this is pretty much you can do with perceptron, where if you have linearly separable values, it is possible to use perceptron to create the boundary and then separate them out. And you can see when you do the iteration right through the EPO count, you can find that the decision boundary keeps shifting between values. Sometimes it will start with this, because majority of the values provided here or here, and then you also have this one here and then this one here. So, it tries to separate this first, and then suddenly when it encounters a value which is belonging to the negative class or the positive class, in this case let us assume that this belongs to the negative class, it will start moving the decision boundary from here to another place, and then you can see that the bias is actually pushing the boundary from the origin, so that it can align with the right boundary line. Okay. So, now it will try to move it, and your W would be in this fashion. You can keep looking at that, right. There is a way you can plot how the error lines are really moving up and down. You can see that it will start from here and then slowly adjust and finally move to the right spot. Okay. So, this is the final one that you will see. Okay. So, what are the limitations as we have been talking about this? It can only separate a linearly separable set. Okay. So, we can only do it based on the misclassification. Right. So, it is a very simple computation model where you can use it for certain purpose. So, it is well suited for your sentiment analysis in the natural language processing.